So the wave function collapsed into a delta function on a point. It is actually the experimental verification that really particles have wave nature. So we have seen electromagnetic waves have particle-like nature, like photons. Then again, in Compton scattering, we have seen that photons behave like bullets, like particles. This is about really a particle that we thought is a particle. For example, electron behaves like waves. Let me start with an electron gun. So tungsten wire ase, etu eta battery di, we are hitting it with a low tension battery. Then this is called thermoionic emission. That's the electron coming out. Then you have another battery. So you basically apply an electric field, and that electric field accelerates the electrons. You know, electric field, when you apply, there is a force, electric field times charge, and it accelerates the electron. If V is the voltage applied, then charge here, E times V, will be the actually energy, half mv square kinetic energy. If you had two plates connected by a battery, so you have an electric field set up here, and any charge here will, so it's an electron, so it will move towards this with some acceleration. Charge time electric field will give you the force. There is a small hole, so electrons are coming out like this. You have a material on which the beam will hit, beam of electrons, and that will be scattered, okay, in many directions. In a certain direction, we have a detector to look, but this detector can move in a circle. So it can move around. Also, this target can move, and you can see the scattered electron beam in various directions. This is nickel target. So initially, when they did the experiment, the expectation based on classical idea that electrons are particles, obviously. The expectations are that the scattered beam, intensity of the scattered beam, will not depend strongly on the direction where they're looking at. So let's say this is the angle phi, let's say, okay? So if I change this, maybe there will be slight variation with angle, not so much. It will be like smeared. It's like you shoot bullets on a metal surface and they're like scattering away in all directions. So angular dependence will not be that much. Secondly, the intensity, which means number of electrons, coming in a direction will not depend on the energy of the electron. So what is the energy of the electron? Actually coming from this high tension battery. Okay, this is high tension battery, this is low tension battery. So if you apply the voltage, if you increase the voltage, there will be more energy, the electrons will have more energy. This again will not, so this, the intensity and the angle. So now again, if you move when you have higher energy or lower energy, there will not be, again, some strong angular dependence. What I mean is, you will not see in a particular angle a peak, and then in another angle, dip like this. No such behavior. We expect like, okay, some smeared behavior. This is based on classical physics. And that's what really they saw for the first time. So everything was fine. But during their experiment, an accident occurred, and some of the air entered the vacuum chamber. So this whole thing should be inside vacuum, of course. You cannot shoot electron in through the air. So this setup must be inside a vacuum. But accidentally some air entered, and air, so nickel got oxidized, okay, nickel oxide. So to clean that up, they heated it. So they heated it, they baked it. And after heating up, with really high temperature, when they cooled it and brought it for the experiment second time, this time they saw something completely different. So around, when they start increasing the voltage, first 40 volt, then 44 volt, and some 54 volt, they start to see, like first, I'll explain what this curve is. So let's say this is the beam falling, okay? This is the point where it hits the nickel target. This graph means, this graph is a plot of distance, so any point, so let's say it will not be smooth. These are points, let's say, your experimental data points, right? You're doing some experiment, so you have some table. So these are your points, let's say. These points are plotted in a way that in this particular angle, what they see is actually the distance. So you are plotting the intensity as a function of angle, and that intensity is represented by how far this is from that point. So this is not like usual plot, where you have, let's say, some angle, so phi, and intensity is like, okay, the intensity is something like this, and then it's increasing and then decreasing. This should be the usual plot. But here, this height, okay, it's small, then higher, then very high, and these things are plotted as a distance from this point. So let's say for some 50 degree, this one is 50 degree. So it's a nice, clever plot, really. Angle and this thing represented in a very, very nice way. So this is the incident beam. If you look at a 50 degree angle, so some beam are coming out, the intensity in that direction is plotted as a distance from this point. So this distance is higher, so it's like more intensity. Okay, this distance is very low, so in this angle they are seeing very less electrons, like that. Okay, so basically if I plot it in a smooth way, this is how it looks like for 40 volts when they set the the high tension voltage at 40 volts. At 44 volts, exactly, again at 50 degree, they start to see this, okay? At 54 volt, they see a sharp this. So exactly along the 50 degree, they looked when the voltage was 54 volts, and they see there is a sharp peak at 50 degree. Okay, so you're moving your detector. Exactly at 50 when you come, you see a high intensity. And then after sometimes there is a drop, sudden drop. So a peak and then a drop and then smooth. So this is what they saw. This is completely against what they expect classically. If the electrons were particles, this should not be how the data should look like. Why this is happening? They asked, and this was not unusual graph, but for the electrons it was unusual. But people had seen this kind of peak in a certain angle, and then again a drop, but for X-rays. Okay, if you did the experiment with X-rays, then there should be a peak and a drop because of another phenomena that is very wave phenomena. It's called diffraction. Diffraction of X-rays give rise to some peaks and then drops, right? You know this from diffraction. Like interference has bands, bright and dark, bright and dark. Diffraction has such like very high intensity and then low, then slightly high, then things like this. So what this means is like if you rotate it, it's like circle here, a bright spot, then a bright spot, then a bright spot like this, like this. This is diffraction. So in a particular angle, and this is for nickel crystal. Okay, I'll tell you what crystal is. And it's seen, so now the question is, why not before and why after baking, after heating it? So one thing people knew, that when you heat up a metal, usually metals are not in, let's say, perfect crystal shape. So you haven't got what the crystal is. So let me first tell you. Crystal is organized arrangements of atoms. Okay, it's the atoms are not like this randomly. In a crystal, atoms are arranged in a nice array. So this, and let's say left like this, perfectly in all directions. So this is called a lattice structure. A very symmetrical, very organized repetition up to the whole crystal structure. But usually the nickel was disorganized. When you heat it, when you heat nickel to very high temperature and cool it down, the whole thing becomes one crystal. And you have this organized structure throughout setup. When that happens, it behaves like, so look at the crystal. If this is a piece, it has then really nice that's how the arrangements become. Sorry. So atoms are arranged in a nice array, and the whole nickel block becomes a whole crystal. Now that is like array of mirrors or glasses. Okay. Now Davis and Germer said, what we are seeing is behaving like X-ray. So if electrons were like X-rays, then they tried to test it. Now we have a formula for such things. So suppose you had planes like this, then there will be, so this was the electron beam, right? But if you had X-ray, it will fall and it will get reflected. So if this is, let's say this is the plane extended, in their case, if nickel was the thing, then at 65 degree, the incident beam was falling. And so it will exactly reflect at again 65 degree. But this was 50 degree they observed, right? Incident and reflected had an angle between 50 degree. So this angle is 50 degree. But the planes of the nickel are in that angle. So this is 65 degree. And so reflected will also be at an angle 65 degree with the plane, with the mirror. So then 65 plus 65 plus 50 will become 180. So you're looking at this direction and you saw a peak exactly at 50 degree. Okay? In that case, what happened? So it gets reflected in this, and then another one gets reflected from this, and these two waves constructively interfere. And so you see a brightness. And when that happens, and in another angle, what happens? They meet destructively. So this is given by something called Bragg's law. M lambda equal to 2d sine theta. Here theta is not this angle, but this angle. Okay, angle with the plane. So theta in our case is 65 degree. This d is the distance between these planes. Okay, so d for nickel was known from X-ray diffraction to be 0.091 nanometers, and theta 65 degree. Now n is called the order of this diffraction. What that means is it can happen due to this thing, but it can cross and go to another level and get reflected again, you know. So that will be n equal to 2. So the brightest one is for n equal to 1. So n 1, 2, 3, 4 like this. So the brightest one is for n equal to 1. So when we put n equal to 1, theta equal to 65 degree, d equal to 0.091 nanometers, then lambda comes out to be around, I think, 0.165 nanometers. Okay? Now, if electron was really behaving like a wave, and if this is diffraction, so we see a brightness in a particular angle, then this formula of X-ray diffraction, you know, X-ray diffraction formula can be applied to this, because this is again wave, and we are seeing diffraction. This is just a theory that they're considering. Okay, let's say electron is behaving like wave. If it did, then we can apply X-ray diffraction formula, and in that case our wavelength of that particular electron has to be this. Now we know if electron really behaves like wave, then the voice said, what should be the wavelength? Right? You know what is the energy of the electron. I told you it's 54 volts applied. So 54 electron volt will be the kinetic energy. Right? So kinetic energy will be supplied by the battery, and this will be 54 electron volts. Right? Okay, so half mv square, this will be half mv square. From this, if you do, mv will become 2m times kinetic energy. And then if you put like the mass of electron 9.1 into 10 to the minus 31, and then this energy, and then convert it into joules using 1.6 into 10 to the minus 19, then you see it will be 4 into 10 to the minus 24, I think, SI units, kg meter per second. Now this is your momentum of the electrons. And if this is momentum, then this particular electron should have a Devoy wavelength h over mv. This is non-relativistic, very slow. So we can just put mv, not gamma equal to almost 1. This turns out to be 0.166 nanometers. Almost the same thing. And so, I mean, what you expected? Yes, really, this is behaving like a wave. Which wave? As exactly the way predicted, that it should be h over mv. And that particular wavelength, with that particular wavelength, have been seen in this experiment. So that's... Oh, half mv square whole tomar kinetic energy. So mv square is about this, and then m square. So md eta multiply kori dim yat. Eta mv square is about, and then root 3. So I mean, experimentally now, this has been proven. So yes, I mean, both the wavelengths, what we see experimentally, if electron was a wave, then this should be the wavelength, using diffraction formula, very wave formula, right? And then this, it matches with what should be the wavelength according to the Voigt, and we're good. Although, I mean, I made it look like very easy, the analysis of the data. It's not that simple like analysis. There are many complications in analyzing the data, but the summary, the result is this. Actually, this particular graph, the plot, when I studied, this was the part I had to spend more time understanding because it was slightly different kind of graph. He plotted, so I mean, I tried to explain. If you did not understand, you can ask and go back, think about this. So you are looking at different angles here, like really angles, instead of plotting theta in this direction, you know. He's plotting theta exactly like this, along with the incident beam. And so in a particular angle, let's say here, when at 50 degree, he is seeing a peak. So that peak he is representing as a long distance from this point. So this point is far. At a smaller angle, he saw very less intensity. So he put the point here. So this distance represents the intensity, and this represents the angle. So that's why you get a graph like this kind of something. Okay. So we got the proof that particles do have waves associated with them. Now, there's another very interesting and really amazing consequence if a particle behaved like wave. Particle in a box. So let's say you put a particle inside a box. So the particle is bouncing back and forth and only one-dimensional motion, let's say. I drew it like this, but it's, let's say, only one-dimensional box. That means just in one line, it's going to and fro. And the walls are infinitely hard. So that means the ball is not losing any energy. So when it hits this wall with momentum P, it gets reflected with exactly the momentum P. It's not losing any energy. So the walls are infinitely hard. Okay. If it's not hard, then the wall will, after it hits, it will slightly go backward. And so some of the energy will get transferred to the wall. Right? So that's why infinitely hard wall taken. The length is L. Now, if there was a wave associated with the particle, then the wave cannot be in any form. Waves inside a box has to be a standing wave. Like strings whose ends are tied. Then you know again, the wave can be either this, at the minimum will be this, or this, and like that. Okay. So on. Waves cannot be spread out outside. Why? Because if wave is outside, what was the wave of? What kind of wave was it? The matter wave, the Voigt wave. Wave of what? It was the wave of probability. So if the wave looks like this, let's say, it means that if you looked at, and this is the x coordinate, let's say x, and this is your wave's mod square. So if psi was the wave, mod psi square, I plotted in this way. Then at this particular point, let's say x equal to some x naught, if there is a peak, if you looked at that particular point, then there will be, the chances of finding the particle there will be more compared to, let's say if you looked here, some other point. So if psi is the Voigt's wave, then mod psi square will give you the probability distribution. So if you like prepared many such particles, all with the same wavelength, same wave function, then if you looked in all of them, then most of the times you will find the particle in most of them here. Very less times here, and almost never here, never here. So basically this wave is a wave of, is related to wave of probability. Probability, if psi was your wave function, let's say, the wave, the Boy wave, right? For example, water wave is a wave of height and all these things. Probability will be proportional to mod psi square. This we discussed. You should go back and watch the lecture again. So if this is the wave of probability and wave really came out of this, not ended here, if it was outside, then it means that there is some non-zero probability. If there was some psi outside, let's say if it was like this, okay, that means what? Here we have some non-zero probability. If you took mod psi square, then there will be some non-zero value here, okay, after length L, here. But it's not possible. We said the walls are infinite. The particle cannot go outside. So if the particle cannot go outside, there should not be any probability of finding it outside. The probability should be absolutely zero. And that means wave cannot exist outside, because the wave represents its probability of finding. And therefore, the only possibility is that the wave should end in the boundary. And this is just standing wave. We already know this. For other waves, we know this. For light, for strings, for sound, you know, organ pipes. Okay, in these cases, what we know is n lambda by 2 equal to L. You know this. It's because this is half lambda equal to L. This is 2 lambda by 2 equal to L, and so on. N equal to 1, 2, 3, blah, blah, blah. So basically your n lambda becomes what? 2L by n, right? Now we know lambda is also h over p, right? So then my p becomes, p is then your nh by 2L, right? So if p is this, we know energy or kinetic energy is p square by 2m, half mv square, right? P square by 2m. So if you did that, m square, h square, 4 times 2, 8, m, L square. And that's the only energy here. There is no other potential inside. There is no other potential, so this is the total energy. So total energy then becomes n square, h square by 8m, L square. This is a very interesting formula. What is n? N is 1, 2, 3 and all these things. Let's call this thing, because this is not changing, h square over 8m L square as, let's say, our E1, okay? If I put n equal to 1, then what? This becomes h square over 8m L square. And this is going to be constant fixed factor. So let's call that E1. So then I can write n squared E1. E1 is h square by 8m L square. For a fixed box, that will be the minimum. And let's call this En. This tells us, remember n equal to 1 is the minimum. This tells us what? That energy cannot be zero for this particle. Minimum it has to be this E1, n equal to 1. Secondly, it tells us energy cannot be continuous any value. It has to be either 1 E1 or 4 E1 or 9 E1 and like that, right? The energy has to be E1 equal to E1, E2 equal to 2 E or 4 E1, E3 equal to 9 E1, and so on. If you plot it, you will get some zero level value, 0, but that particle will not have zero energy. The starting will be E1, some height from 0. The second one will be 4 times. 2, 3, 4 here. E2 equal to 4E1. Or just, yeah, okay. And then you will have 9. So this is 4, this is 8, here 9. And so on. You know, there will be certain discrete energy levels that the particle inside the box can have. It cannot have any energy. But this is very unusual because classically, we know if this is a box, we could put a ball here perfectly and it will be at rest. Okay? Classically, with a ball, we treat the ball like a particle. And if this was a room, let's say, or like you can, to make it one-dimensional box, what you can do is take a really tight string and put a bead. You know what a bead is? Like a necklace of thakajanaka round. So the bead, it can move freely, but in one dimension. We know we can put it at rest. It is at rest, so it has zero energy. Right? What is happening? This kind of situation, it's saying that no, that's not possible. A particle cannot have zero energy. Also, the bead, you can give it any energy, right? Any amount of energy and it will have that kinetic energy. Slightly more. Who said it? I mean, we have never seen that it should have some discrete. So you push it, it's not moving. It's like, imagine if the macroscopic world behaves like this, then it will be like this. I push it, nothing happens. So first of all, it is not at rest. It cannot be at rest. Some slow velocity will have to be there. Next, I push it, give it some energy, it will not take it. But after some time, like if I give it a particular amount of energy, that's 4 times its ground level energy, then it starts moving with a faster speed now. Then again I give it energy, nothing happens. Then I give exactly 9 times its ground level energy push, then it takes it. But this is not seen classically. We can give it any value and it takes and lets it speed. So what is happening here? That is not wrong. Both are true actually. The only thing is that look at H. H is very small. H is extremely small. It's 10 to the power 6.625 into 10 to the power 34. And then square of that. The to the power minus 64, 68. Oh, sorry, yeah. And so if you really want to find something measurable, the denominator should also be very small. And in case of tiny things like electrons, yes, mass is 10 to the power minus 31. This L has to be nanometers. Then only these tiny boxes, nanometers, so an atomic size, you will see this kind of effect. When you take really big box, I'll give you a problem, and you have a particle with higher mass and a big like 10 centimeters long box, you will see that you will find, you will apply this formula. And if you put n equal to 1, and this h value, and the ls in centimeters, m in, let's say, grams, this value comes out to be so small, and if you try to convert it into some velocity from energy, using half mv squared, you'll see that that velocity is not measurable, okay? It will be some 10 to the minus a huge number, meter per second. That's exactly at rest. Like it will take maybe millions of years to move from here to here. So that's at rest. That's why we don't see, we see it's at rest. Secondly, n equal to 2, same thing, nothing will change, okay? So it will seem like, so when you give it slight push, it will take it classically, right? It will take it and it will start moving. Why it took it? Because it will obviously match with some level. Because it's tiny, tiny, tiny values, the difference with one level and the other is not much. So if it really starts moving and you see the movement, that energy will correspond to n equal to some huge number, 10 to the power something. So that's why classically it looks like, no, it's not, nothing is discrete, it has a continuous level. But that's just because there is no difference between some n value and the other value. The difference between the two energy is classically indistinguishable. So you don't see anything discrete. But in case of very microscopic things, you will see this how you send a light inside this box of this particular energy, is this gap, and it will jump to this level. Or you excite it and then you observe what light is coming out. You will see that some of them jumping to this level and sending you, a wave, and you measure the wavelength. And you see this particular gap, delta E equal to some h mu. This delta E prime, E3 minus E1, another. You know this from atomic or chemistry really. Hydrogen's atoms levels. It is like that. Now this was a simple example of particle inside a box. In any situation where you trap a particle, it can be, for example, hydrogen atom, where the electron is trapped. How? Due to the Coulomb's force. The nucleus is pulling the electron, and that is like sort of a box. But the walls are not, of course, infinitely hard. Okay, it's kind of soft. It will be like this. Why? Because, sorry, not like this. Like this. Because Coulomb's law is 1 over r square. So you plotted the potential. It will be at r equal to 0, it will be minus infinity. Because it is attractive force between nucleus and the electron. So if you plotted the potential, it will look like this. At r equal to infinity, what will happen? 1 over r square will be 0. So at infinity, there will be no potential. At r equal to 0, it will be minus infinity. So this is how the box will look like. It's obviously not a box, but it is a trap. Just like the box, it is a trap. And if there is a trap, the wave function cannot be everywhere. I just told you. This potential will forbid electron from going out. And if electron cannot go out, its probability should be 0 outside, or very less. And that's why this kind of situation will arise. And as a result, again, the consequence, you will see a integer coming into the picture. And once again, the energy cannot be 0, and the energy level will be discrete. And this discrete thing is called quantization. So this is where the quantum mechanics is coming. Everywhere you see discrete things are coming into picture, not continuous anymore. This simple example of a box, just a box, and it has to be a wave, therefore it has to be inside. So we must have standing waves like this, and this gave us the result that actually matches pretty well with experiments. We don't know how the exact waves are. For that will come later, to Schrodinger wave equation, all these things. But this simple thing, taking this lambda equal to h over p and the standing wave condition, gave you how the energy levels should look like. Okay, and now you can see the spectra coming out of those. So if there was an electron inside this box, that electron could get excited. And then if you looked, you will see that. So if you sent some energy, that difference like 4E1 minus E1, exactly that difference, if you send h nu equal to that difference of, light with that particular frequency, that h nu will give you exactly this gap. So let's say E1 is, just for simplicity, let's say h square over 8 ml square is 1. Then your E1 will be 1, E2 will be 4, right? In some unit, let's say. And if you gave 4 equal to h nu, this particular nu, if you divide it by h, and that, I mean light with that frequency, it will absorb and will jump to the next level. And after some time, if you kept looking, you will see that it will jump back and that same photon will come out. Then you send some energy which is 4.5, let's say, units, and the light will just pass through, it will not accept it. Once you send the energy exactly 9 minus 1 equal to 8, and you see that it took the wave, the photon, and it jumped to the next level. So that's how you know that levels are discrete. Anyway, yeah. A few minutes. Uncertainty principle, I just want to introduce. So when we have waves, we have uncertainty associated. A wave is what? It's spread out, okay? And in this case, we have a wave packet, a group of waves. You know, from the last class that I proved that the wave is like a packet of waves. It's like a lot of waves if you interfered and made a wave packet. Wave packets looks like this, let's say. So if you had a string and you just plucked it, then a wave like this will travel. It will move across. This is an example of wave packet. Now the wave packet, that's of this shape. It still has some spread, right? It has some delta x. It's not like this that we know, oh, okay. And I told you again, let me tell you again, this is the wave of, in case of the Boy waves, matter waves, this represents the probability. So if this is the wave, it means the particle most of the time will be found at this position. It will never be found here and here. It's flat zero, okay? It will be found here and here sometimes, but very less, but mostly around here. So that's probability. But that means we don't exactly know where it is, right? We know, okay, it's here. Inside this delta x, it's somewhere. And I can tell you, like here, it will be most of the time. But that does not mean, this probability is really high at this point. But you can still find it here, right? It's non-zero, but okay, here it will not find it. So it's somewhere here. So we have introduced an uncertainty in its position, right? We don't know anymore where exactly it is. Like classical, we know, okay, the chalk is here, x equal to some value from that wall, let's say. But now we're saying, okay, it may be here. I mean, it will be found here most of the time. But maybe, I mean, if you do the experiment, you might not find. But if you repeated the experiment, most of the time you will find it here, but sometimes also there. This kind of statements, uncertainty. And, okay, what kind of wave is this? What is the wavelength? Oh, I don't know. I mean, how will you measure wavelength with this kind of wave? You need at least a few ripples to calculate the wavelength properly, right? A few cycles. Then you can take average over them and say, okay, this is on the average the wavelength. At least if I give you this, you know, okay, yeah, I mean, I can do this and then with this and then I can take an average. This is the wavelength. One depth to the other, that's the wavelength. But in this kind of situation, I don't know. But at least the uncertainty on position is less because delta x is very small. But lambda, I don't know. What lambda is? Lambda is h over p. So I don't know lambda, I don't know p. So I know the x quite well, not perfectly, but delta x is very small. So like let's say a few nanometers. But then wavelength, I don't know. Momentum, very uncertain. No idea. Now I give you another wave. This time wavelength, oh nice, perfectly. Very precise. Well measured, let's say. That means h over p. That means p is very certain. But on the other hand now, your delta x is large. Delta x is large. That means uncertainty in position is large now. I don't know where it is. I mean, at least it was in a few nanometers. Now in a large space, it could be anywhere with some non-zero probability. Okay, here may be flat again, here flat, but it's huge. So you see, like when you know the wavelength well, you don't know where it is. And when you know, so which means when you know the momentum, you don't know where the position is, exact position, what the exact position is. When you know the exact position more or less, quite well, not perfect still, unless it becomes really like this, then you know. But I will show you this example also. I don't know what lambda, so I don't know what the momentum is. So there is always an uncertainty between x and p. If we know x very well, we don't know p very well. If we know p very well, and we don't know x very well, we know p very well. And if we try to measure both equally, then we don't know both. Okay? Maybe minimum and minimum. Lambda perfectly হয় যেতিয়া sine wave or নিচিনা wave আছে, then আমি জানো what is lambda. Lambda মানে কি? এটা wave repeat কৰিব তাৰ exactly. মানে এটা intervalৰ পিছত it will repeat itself perfectly. Yes. So if this is the wave, only in these cases we know what lambda. Lambda is not even defined in this. Where is the repetition really? After one and then it's flat. There is no repetition. Okay, so it turns out that if the shape of the wave was like, it's called bell shape or Gaussian shape. You know what is a Gaussian shape is? It's like this. Sorry. Some e to the power minus some ax square function. If the wave function had Gaussian shape, for that turned out the del x and del p were equal and they were the minimum possible. For any other shape you take, one of them will be out of control, very, very big. The other one may be small. So for example, what we can do is always if we have a wave, psi of x, we can express, I'll tell you what that means, it in terms of wave number. It's called Fourier transform. You had Fourier transform. Gk and then some sine kx dx, let's say. This is just a plain Fourier transform. Okay? You had some function, you did these things for a box, remember? So this box, do you remember this box can be written as a sum of, then it started to become, so this and so on. And it started, if you take 3 or 4 of them, just 3 or 4 of them, and you see it started to become like, and then you took maybe a few more, and then it became like, and then you took a lot of, you know, sine waves, and it started to become like a box. So this is what it is, just a Fourier transform from x space to k space. K is related to momentum and is related to wavelength. K is 2 pi by lambda. And you know lambda is related to p. Now, so this is called, this gk is a Fourier transform of psi x. Okay? So if psi x is a wave function that looked like this, then gk looks like this. Is this, x is this. So very uncertain in x, very certain in k, which means very certain in momentum. If x was like very certain delta function, turns out k is like this. very uncertain. If you only take psi x to be a Gaussian, turns out your GK is also a Gaussian. And so it has been seen that in a particular way, if you calculate, so what is this delta x, the spread? How do we measure spread? One such measure is standard deviation. If you had some data, x equal to some value x1, x2, blah, blah, some values xn, then if the mean value of this, you know how to calculate mean? Mean value of this, let's say if it is mu, then standard deviation is how much the points are away from the mean, right? If something has a deviation 0, means all the points are exactly at the mean value. 4, 4, 4, 4, 4, 4, 4, 4, 4. That means everything is 4, mean value is 4, and there is no spread. If it's 4, 4.1, 3.9, so it has very less spread. But if the numbers are like 1, 2, 10, 50, 4, then you know the mean will be somewhere, but the spread will be everywhere. So that spread is measured as standard deviation equal to square root of your this mean value minus x whole square, this xi, and then 1 to n, 1 over n. That's standard deviation. It's a measure of how spread they are. You know this very well from, like, if I don't do square, then on both sides there will be equally spread. So plus minus cancel out, it will become 0. Negative, positive, negative. Sometimes the point will be on the other side of mean, sometimes the point will be less than mean, and so 0. So that's why we take a square and the square root, and it gives you a measure of spread. So if you used that definition as a measure of your spread of the wave function, okay, you know, I give you a wave function, you know the mean, and you know all the points. Calculate this standard deviation and call that delta x. Similarly, for this space, calculate for the corresponding, psi x, calculate the GK, plot the psi x, plot the GK, and you know the mean value, calculate this delta x, calculate the delta k. You will see that for a Gaussian, if this was a Gaussian, then del x times delta k will turn out to be half, exactly. And any other shape you take, any other, you will see that it's always greater than half. Only in case of Gaussian it's equal to half, otherwise this product is greater than half. So in general we write greater than equal to half if we consider any kind of shape. And that's actually your uncertainty principle. If you replace k by corresponding p, then it will become h cut by 2. H cut, or h cross is h over 2 pi. Okay? Because p is actually h cross k. So that's your uncertainty principle initial introduction. So you see that uncertainty principle is, the origin of uncertainty principle is coming from waves. We already know uncertainty in waves. And so if particles have a wave nature, then uncertainty is inevitable. It will come. And it turns out that uncertainty is not because we cannot measure. You have to understand this. It's not because that we cannot measure the position well. We are bad at experimentation. No, the nature is like that. The universe is designed like that, at least that much we know so far from all the experiments. That universe will not allow you to know. Because it is wave, so it's by design. You just cannot measure. Because it's not that you cannot measure. Precise location does not exist. If something is a wave, that means it's somewhere in that region where this wave is spread out. So it's this information of precise location is not there. In the last class, I introduced you that three kind of views. Where the particle? So the particle was found somewhere. Where was the particle before the experimentation? It was not. It was probably there. It was not there. But that's not the case. Our experiment made it to be there. Okay, the wave function was like this, something like this. Our experiment changed that wave function into a delta function. So the wave function collapsed into a delta function on a point. And immediately after that, if you calculate, you will find it again there because it's a delta function now. So your wave function is a delta function. Obviously, it will be precisely located there. So the thing is, nature behaves like that. An electron is nowhere precisely. We don't know where it is. We just know that its probability is spread out. This is how the nature is. Okay? At least the mathematics is like this. And because in every experiment, this mathematical result came true, so we know nature must be behaving like this. So it's not like, oh, we can't measure this precisely. If there was like an excellent machine, like excellent future machine, with that we could measure X and P precise. No. It's not the fault of the machine. The nature is like that.